Hello everyone, the problem that we're looking at today is the USACO 2024 December contest silver problem 2 of deforestation. And actually, before we start, I'm going to say this problem is a pretty painful memory for me. Because, first of all, from the name, you can tell that this is the most recent contest that happened less than a month ago. And it did not go well for me. For me, I got 633 with the cutoff being 700, so I was 70 points off, actually 67 points off. And if I solved this problem during contest, I would have gotten promoted because this problem is actually pretty hard, but with my method, it's actually pretty easy. I totally could have gotten it if I spent like 5 more minutes on it during the contest. But in contest, after spending 20 minutes and getting the second subtask being the first 5 test cases, I don't know what happened. I just chose to give up on it, and then I went to problem 3. I was able to think of the correct solution for problem 3, but I did not completely solve it. I'm pretty sure most of the test cases, but not enough to get me promoted with only half of the points from this problem. And when I came back to it after the contest, I realized that if I spend maybe 5 or 10 more minutes on it, I could have solved it because the algorithm that I was able to implement after contest was not that complicated, and it did not take me that long to think of it or write it out. So this is the algorithm that I'm going to explain today, and it's the method using the binary index tree. So now we can actually start. You can pause the video first and look at this problem yourself. All right, so basically you're given n spots for trees, and then you have k restrictions, and each restriction states that there must be at least ti trees within the segment li to ri. And you're given that there's only xi positions with trees, and now you're trying to cut down the trees, still satisfying the restrictions. And you can pause the video once again and think about this yourself, with at most 10 to the 5th power, which is 100,000 trees and 100,000 restrictions. All right, I assume we gave this problem a try. And I would say this is actually not that difficult if you know binary index tree, which a lot of you guys, if you're actual silver people, you're not supposed to know this because it's definitely gold, sometimes even platinum algorithm, binary index tree, or segment tree. But I'm pretty sure there's a lot more people like me who knows very advanced algorithms and are just kind of stupid, just like me, and can't get the gold. Anyways, how do we do this with binary index tree? So the algorithm I'm using today is actually kind of reverse of what the problem is asking, because the problem is asking for us to cut down trees, but my algorithm is actually growing trees. And I'm considering all these xi spots as potential tree spots where I can choose to grow my trees or not. And now we're trying to grow the least trees to satisfy the restrictions. And to achieve that, we can use a method called sorting through the right end, because I actually done a problem kind of like this before, still also with restrictions and growing stuff. So this just kind of a classical trick. I would not say classical trick, but if you've done enough problems, you probably know this. So say we have all these regions, we sort them through right end. So you can see that's what I'm doing right now. We sort them through right end. And now since the right end is increasing, for every region, say we're considering the first region right now, and then there's a few spots where it can grow trees. They're not actual trees, so I'm just going to draw like pits here. Those are spots that we can potentially grow trees in. No, actually, we're going to make them all on the same plane. All right. And now you can basically see which trees are included in which regions, right? And now, how do we decide which trees to grow? Well, if we know that this region still needs, say, 2 trees, well, we have to grow these 2 to be optimal. Because why? Because we're trying to make those trees satisfy as many regions as possible so we can grow the least number of them. And we know that this region is, out of all the regions that are not satisfied, with the leftmost right endpoint, right? Because all the regions with right endpoint to the left of it has already been processed, and we assume that it's already satisfied. So we're only trying to make those trees satisfy as many later regions as possible, and we know for every single later region it has a greater index for the right end, right? So we know that we always grow the rightmost trees to satisfy this region so that we can satisfy all of these regions because they all have greater right end. And knowing that, this is actually kind of like a greedy algorithm that we can use now, because every single time we just, for every region, just check how many trees already in it. Say after we grow these 2, for this region that the restriction is like 3, we know that we only have to grow 1 more tree in this region because we already have 2 from before. And then we just do this greedy algorithm for every single region, and then we have an algorithm with complexity of n times k, right? Because for every k restrictions, we might have to check through every single tree, n of them, to make sure to check how many trees we already have from previous regions. However, NK is not going to be enough for this problem because that's the algorithm that I implemented during the contest, and I got the first 5 test cases because NK is 1000. And even though this greedy is already took some thinking and some time, for me it took about 25 minutes to actually get the code out, it's still not enough because it's NK. So what do we do now? Well, notice that most of the complexity, because it's NK and the N comes from checking for how many trees already been grown in this region. Because otherwise, if we already know how many trees in this region, we can just start growing from the end, and every tree can only be grew once, and there's only n trees, so the total complexity of growing trees is going to be on, and then checking each region is also okay. So it's on plus k in total, right? So we just need something to quickly help us find the number of elements within a region, right? We're just going to treat each tree as an element. We're trying to find the number of elements in, say, this region right now. And what does that remind us of? If you know it, it's going to be either segment tree or binary index tree. For binary index tree, you can find all the elements with values less than this and then less than this, and then you subtract the number of elements less than this and the number of elements less than that, and you get the number of elements between them, right? That's how binary index tree works when finding the number of elements within a region, and a segment tree is even easier. But I'm not going to explain the segment tree way here, but I trust if you know this, you'll probably know how to solve it with the segment tree now. And for binary index tree, we actually also need to maintain a multi-set for each tree. Oh, and also the reason we're using binary index tree is also because we're constantly adding or removing elements. No, not removing. We're constantly adding elements because each tree we're growing it while we're iterating through every single region. So it's like adding elements, and the only data structure that support both queries and modifying in log complexity, which is what we need right now, are segment tree or binary index tree or BIT. So my algorithm today uses BIT because it's way easier to write. The code is way shorter, and I just prefer it. So this is my algorithm for BIT here. First of all, we need to discretize because the trees and the regions are very spread out to 1 and we can't have the binary index tree actually maintaining elements up to the size of 10 to the 9th power. So we have to discretize it using an event array. Every single event, like left region, right region, tree spot, we store it into the array, and then standard discretizing. We all know how to do that, right? Hopefully. So that's discretizing. And then now we have all the trees and regions packed together. If you know what discretizing means, that's what it means. You pack everything together, so everything is next to each other. And now we have at most 2 E5 elements because it's n trees. No, actually 3 E5, 3 times 10 to the 5th power. Because there's 10 to the 5th power trees, and then 2 times 10 to the 5th power left endpoint or right endpoint. So in total, there's going to be 300,000 of them. So that's small enough for a binary index tree to maintain, and we have a multi-set because it never said that trees spot doesn't repeat, so we could have several trees on the same spot, so we had to use a multi-set, not set. So after using a multi-set for storing the trees, erasing a tree is, from that we know that next time we can't grow on this tree because this tree's already been grown by the previous region. We have to grow the tree before that, which satisfies less region because our other regions have greater YM, but we can't. But that's the only thing we can do because this tree is already grown, right? And for the binary index tree, here it's just a standard BIT add and then get. I'm not gonna explain entirely how BIT works. I'm just gonna tell you it's a data structure that allows you to modify by inserting elements or erasing element in log complexity and find the number of elements that are less than a certain value also in log complexity, which is really helpful, especially in gold, but in silver, just like I said to myself in the code, this is like using a nuclear weapon on flight because BIT is like advanced even for gold, I'm pretty sure. And this is silver. This is silver P2. So we really shouldn't be doing this. But there is I think, priority queue greedy method that I could not think of. I still haven't solved this problem using that method because I'm way too busy doing other stuff, preparing for January, and I just didn't think I just didn't have time. I've been mocking contests a lot, and it doesn't matter. So this is my implementation. The main code is not that difficult. The binary index tree isn't either. If you know how binary index tree works, you should be able to understand this code that I will be posting down in the comments with a lot of explanations in the middle. So I think looking at this code, if you don't understand yet, looking at this code will definitely help you. All right. So now when we come back to our question today, the USACO 2024 December contest silver problem 2 of deforestation. first of all, the first thing that you need to know this is that actually cutting down trees is pretty difficult for us to think about. So we're gonna think about it the reverse way of growing trees. We're gonna grow the least trees. And now, secondly, you have to know that if we sort by right end, we have a greedy algorithm that tells us exactly which trees to cut down. However, after realizing that this is NK complexity, we utilize a different algorithm called binary index tree to help us find the number of trees already growing in each region so that we can quickly determine how many trees and which trees we need to cut down for this region. And no, we need to grow for this region. And that's how many we need to cut down. It's just the total number of trees minus the ones that we need to grow are those that we can cut down. So hopefully this video helped, and hopefully after this you know how to solve the 2024 December contest silver problem 2 of deforestation. And as I said, this is painful memory for me because I didn't pass this contest, but I hope you guys are also all working really hard for the January contest, and hopefully we all get a promotion we wanted in 18 days, I guess. Thank you for watching this video. See you. Alright, now that was a problem for today. That was a pretty painful problem, pretty painful memory, and here comes the grind report for today. If you guys already know the routine, after the problem review, it's grind report, so I can keep track of myself, and you guys can help me keep track of how I'm grinding for the January contest, I guess. And hopefully you guys are also grinding for the January contest if you didn't yet got promoted in the December, because I know a lot of you guys did, because I was ranked 1000 with only 7.70 points off. Then I guess probably 800, 900 got promoted or something, but doesn't matter. So basically, my grinding today was okay because it's the first day of school. First of all, I mocked the. It's not really mocking because I already did one of the problems, but it's the 2019 February contest, and one of them I already did. The other one, I think I already knew the answer for it, but never implemented the code. And the last one is just brand new, but still took me 2 hours, some reason, I don't know. The first problem, even though I already knew the answer, the code was pretty complicated, and that was probably why I didn't implement it the first time I did it. And then the last problem also had a few bugs, so 2 hours, not too good. The last problem, no, the second, that's for 2 hours. And then I also I didn't actually mock the contest. I just looked at the 2019 U.S. Open, and I was not expecting to get stuck on the first problem for a 2019 silver contest. Because usually 2019 and years before that, I'm supposed to cook them. They're really, really easy, but I still got stuck on one, and it was a really good problem. It was the 2019 U.S. Open problem 1 of left out, and it's a pretty good problem. U.S. Open, even though it's U.S. Open, it's still 2019 and it's still silver. They're not supposed to be hard. So this is left out. I solved it, obviously. It took me an hour and 30 minutes, not good at all. But I solved it. It's a pretty interesting problem where you just have to make a lot of observations and notices to be able to solve it. But overall, I was still expecting to be able to solve it. If I want to make it this January, I should be able to solve every single silver problem that ever exists on USACO, because that's just how much the difficulty is increasing by not even every single year, but every single contest. So yeah, that's the grinding for today. In total, I grinded for, I'm pretty sure, 3 hours and 45 minutes, 2 hours and 15 for the first contest, and then 1 hour and 30 for this problem. So first day of school for second semester, I guess that's good enough. And I hope you guys are also still studying hard now that school started, and hopefully you get the promotion you want in January through starting hard. Okay, that's the actual end of this video now. Thank you so much for watching, and I'll see you tomorrow.